Hello, Gen Chem friends. Thank you for joining me again today to talk more about the quantum mechanical model of the atom. Because now we're really going to get into the meat of that part of the theory that deals with probabilities and wave functions. What does all of that mean, and how does that all relate to where an electron is in an atom? So if you think back to our previous conversations, we now know that electrons have particle-like properties. We saw that with the photoelectric effect. We were able to calculate energy associated with transitions of those electrons, particularly in a hydrogen atom. But we also saw that electrons have wave-like properties. That was seen in the double-slit experiment model of the atom. And we also saw that as wonderful as the Bohr model is of the atom, that thought about electrons mainly as particles, that model in and of itself was insufficient with with atoms that have more than one electron. So all of that, along with the uncertainty principle that we talked about in the previous video, led to Erwin Schrödinger to craft something called a wave function. A wave function is a bunch of mathematical equations that predict the energy and the position of an electron where it is most likely to be found. And we say most likely because with the uncertainty principle, we learned that we cannot, with equal accuracy and precision, determine the speed and position of an electron. So Erwin he got a Nobel Prize for this as well, was able to craft an equation using information from the Bohr model, using information from de Broglie and from the double-slit experiment, to explain the wave-like behavior of electrons and use that to predict where an electron is in an atom. So these wave-like equations, if I can get to the next slide, have to do with probability. And I use this, if you had me for intro chem, you saw this, you have seen this figure before. If you think about probability with regards, not so much to an electron right now, but think about it with regards to where an apple falls from a tree. If I was to make a prediction as to where an apple was to fall from the tree, I could say, I can make some sort of estimation as to where it would fall, but I wouldn't know exactly where it fell. I would have some sort of sense as to where it fell based upon where it is located from the distance from the trunk. So there is a higher there's a particular distance from the trunk where there's a higher probability of finding an apple, obviously depending upon the tree. That concept, think about it similarly, but in terms of 3 dimensions for an atom. There is a certain probability where it is most likely to find an electron in an atom, depending upon the element that you are dealing with. That probability is expressed in this wave function that Erwin Schrödinger derived. Now, these wave functions, as you see, are pretty hairy, pretty complicated. You talk about the mathematics involved with them much more in physical chemistry classes, and you may actually talk about them if you go on in higher level math classes like Calc 3 and specifically differential equations. So we're not going to actually do calculus associated with these wave equations because the math is complex. What you need to take away from this lecture, from this unit, are some concepts associated with wave equations and being able to determine solutions from them using some more elementary math, which we'll talk about shortly. What do you need to take away from this slide? You should know that Wave functions describe not only the energy that an electron has, but it also explains the regions of space where the electron is most likely to be found. These regions of space where the electron is most likely to be found, those regions are called orbitals. So if you remember back in the Bohr model of the atom, electrons were in specific paths called orbits, regions that went around the nucleus. In the quantum mechanical model of the atom, we have moved from orbits to orbitals, regions of space where an electron is most likely to be found. These orbitals are specific to particular atoms. I just give an example here of the wave function for an electron in hydrogen. Don't need to memorize that. I just show it as an example. But those are the concepts that you should take away from this slide with regards to wave functions. You should specifically also know that when you square a wave function, that is what actually gives the probability of where an electron is. That square of the wave function gives the orbitals, the shapes of the regions where the electron is. These orbitals that we'll define a little more in subsequent lectures, these orbitals can be represented as three-dimensional shapes as either dot pictures or boundary surfaces. You will see both of these in your online homework and in lecture. A dot picture essentially from the square of a wave function basically shows you where the density of an electron is more concentrated. So in this dot picture on the left, the majority of the electron density is in the center. Boundary surfaces represent more of a region of space, and it shows more of the shape. And we will see that depending upon the orbital that you are dealing with, the boundary surface, the shape, will change. So you should know that wave functions dictate energy and probability of where an electron is in an atom. Specifically, the square of the wave function gives us the orbital. In the next video, we're going to talk about the solutions to a wave function. We're not going to do calculus, we're not going to do differential equations, but we're going to talk about the solutions that come from the square of the wave function and what those solutions tell us with regards to energy and shape and orientation of that orbital.